So once we have looked at our equimolar counter diffusion and we have looked at unimolecular diffusion, the next thing that we want to look at is the diffusion coefficient itself. Until this point, all the examples that we have solved, we have actually been given the diffusion coefficient, or also known as diffusivity. Okay, you can call it diffusion coefficient or diffusivity. Now, to find this diffusion coefficient, we actually run experiments. So these experiments has been run before by a lot of scientists before this. So the diffusivity of some common gases that diffuses into air. So if you have, let's say, nitrogen into air, benzene into air, methane into air, at 0 degrees Celsius and 1 atm. So remember, this is also 0 degrees Celsius and 1 atm is also known as STP, standard temperature and pressure. So if there is a problem, a question that says that the system is at STP, you should automatically know that the temperature is 0 degrees Celsius and the pressure is 1 atm. Okay, so some of the diffusion coefficient can be found in Appendix 11 in our reference book, McCabe and Smith. So I'll try to upload this in our e-learning as well. And if you are not given, if the diffusion coefficient for other gases are not given, you can calculate it either by using this equation. Okay, so this is the first equation developed by Chang and Otmaris. Okay, so you can look at here. In order for us to calculate the DAB, we need to know the temperature, we need to know the molecular weight of component A, molecular weight of component B, the pressure of the system. TCA is the critical temperature of component A, TCB is the critical temperature of component B, VCA and VCB is the critical molar volume of component A and B. So all these values are given in the appendix. The only thing you need to know is that how to get those values and then put it in this equation and then solve this equation. Okay, that is the first equation that we can use to find the diffusion coefficient of in-gaseous system. Okay, so this is an example of Appendix 11 that I mentioned just now. So you can see here diffusivity for gases that is diffusing in air, meaning that acetic acid is your component A and air is component B. So if you have acetic acid and air, acetic acid diffusing into air, this is your diffusion coefficient. But remember, the unit here is feet squared per hour. So if you want to use it, in our case, most of the time we'll be using meters squared per second. So you must be able to change it from feet squared per hour into meters squared per second. Okay, and then again here, 0 degrees Celsius and 1 atm. So this is only valid for 0 degrees Celsius and 1 atm. If you have other temperature, if let's say you have 25 degrees Celsius and 1 atm, this value are not valid anymore. You have to do some modification to the value. Okay. The second equation, and usually we'll be focusing more on this equation, is this Chapman and Enskog equation that predicts the diffusion coefficient. So here again, DAB is our diffusion coefficient, T is our system temperature, T must always be in Kelvin. That's why if you see here the description that I put here, temperature bracket Kelvin. If you have the temperature is in degrees Celsius, you have to change the temperature into Kelvin. MA and B is our molecular weight of component A and component B. P is the pressure of the system and it must be in atm. Okay, and then sigma AB squared. So this value is the average collision diameter, and then we have omega D, which is your collision integral based on this Lennard-Jones potential. And then K is your Boltzmann constant, and sigma here is your Lennard-Jones, phi is your Lennard-Jones force constant. And in order for you to find phi AB, this is the formula. Okay, so we will be focusing on this equation, on how to get a diffusion coefficient for a system that has component A and component B. So based on this equation, we will be using it to find the value of diffusion coefficient. So if you look at here, temperature, no problem. Molecular weight of A and B, no problem. Pressure also no problem. The only issue here is this two value, the sigma AB and the omega T. So in order for you to find these two values, you will have to use the appendix. Okay, so these are appendix that I've taken from our reference book. So I'll also put this in our e-learning. Okay, so if you see here, in order for you to find the value of omega, you will need to know the value of kT per phi 12. Okay, so our main focus is to find the value of omega d. In order for us to find the value of omega d, you have to know this value first. Okay, in order for you to find this value, you have to have a component. Okay, so this value is specific for a component. So let's say I tell you that we have a question to find a diffusion coefficient. Okay, so let's say this is the example. Okay, predict the volumetric diffusion for benzene in air at 100 degrees Celsius and 2 atm. Okay, and we are actually using this equation. So if you look at this equation, we want to find the diffusion coefficient for benzene into air. We know the temperature was given 100 degrees Celsius. We can find the molecular weight of benzene, molecular weight of air, and we know the pressure. Okay, so now the issue here is that we need to find the value of sigma squared AB and then omega D. Okay, these are the two problematic things that we need to find. So the first thing, let's say sigma is a little bit easy. In order for you to find the value of sigma AB, it's just that you have to find the value of sigma A plus sigma B over 2. So you get the value of sigma AB. So if you want to get sigma AB squared, you just square this 2. Okay, so this is a simple and direct. How do you find the sigma A and B? So depending on your coefficient. So if you look at here, we'll have the value of sigma for almost all the things. So you can say this is the value of sigma for air. So this is your B component. My benzene value. So this is the value of component A. So now I know the sigma of A and sigma of B. So I can easily find the value of sigma AB squared. So that is done. The issue here is that I want to find the value of omega D. Okay, so if you look at here, in order for me to find omega D, I have to find kT epsilon 12. Okay, so I'll just write here. In order for me to find omega D, I first need to find the value of kT over epsilon 12. Or in our case, I can say that it's going to be kT epsilon AB. So in order for me to find epsilon AB, this is the formula for epsilon AB. Epsilon AB is equal to square root of epsilon A times square root of epsilon B. Okay, so this is the formula. But if you look at our table, the Lennard-Jones force constant, it is given us in epsilon over K. Okay, the value is given us is epsilon over k. Now, in order for us to find the value of epsilon over k, so we have to do some modification. The modification is that we know that to find epsilon AB must be square root of epsilon A over epsilon B. Now, if I put here epsilon A over K times epsilon B over K, so I'm actually finding epsilon AB over K. Okay, so we just modify so that we can actually use this term here. Now that I have found my epsilon AB over K, but here, in order for me to find the value of omega, I will need to find KT over epsilon and AB. So what I need to do here is that I have to do, after I've gotten this value, so I just put it here. After I've gotten this value, I just change, I put 1 over epsilon AB over K. So I just inverse the value, so I'll get here is equal to K over epsilon AB, and then I can just times with the value of temperature in Kelvin. So I will get here KT over epsilon AB. And once I have gotten this value, I can just use interpolation to find the exact value of my omega d. So once I have gotten the value of omega d, it's just a matter of substituting all the equation, and then you'll get the value of DAB.